testing of Hess Law at the Kenya Certificate of Secondary Education in the recent past. Now we realize that in 2011, Hess Law was tested in Chemistry Paper 2 as question number 7 for 11 marks. We will also go ahead to look at the year 2013 when Hess Law was again tested in Chemistry Paper 2. This time round, it was in question number 2, part A, for 5 marks. Let us begin this video with question number 7 for the year 2011 Chemistry Paper 2. Part A, we were asked to define molar heat of combustion. And molar heat of combustion is simply the heat change which occurs, when one mole of a substance is burnt. When 1 mole of a substance is burnt in excess oxygen. This would be the definition of the heat of combustion of a substance, or what we normally call the enthalpy of combustion of a substance. For part B, we were then asked to state Hess Law. And as we said in our previous video, Hess Law states that the heat evolved or absorbed in a chemical change. The heat evolved or absorbed in a chemical change is the same whether the change occurs in one step or through many steps. That is the simplified definition of our Hess Law as discussed in our previous video. Part C of the question told us that we were supposed to use the following standard enthalpies of combustion of graphite, hydrogen, and enthalpy of formation of propane. So this is the enthalpy of combustion of graphite given as negative 393 kilojoules per mole, enthalpy of combustion of hydrogen given as negative 286 kilojoules per mole, and then we have enthalpy of formation of propane given as negative 104 kilojoules per mole. So using this data, the first question now asked us to write the equation for the formation of propane. So formation of propane would mean we have to form propane from its constituent elements. The constituent elements of propane is carbon and hydrogen in their standard states. So when you react carbon and hydrogen, we get propane. This would be the equation for the formation of propane. And as we balance, we need to make sure that we form only 1 mole of propane on the right hand side. So that would mean we balance with a 4 on hydrogen and a 3 on carbon for that mark. We proceed to the rest of part C questions. In Roman 2 of part C, we are asked to draw an energy cycle diagram that links the heat of formation of propane with heat of combustion of propane, heat of combustion of graphite, and heat of combustion of hydrogen. Now, before we do this, it is always good we write equations for all the heat types that have been mentioned in our question. We begin with the first one, which is heat of formation of propane. We have just written it on the other question. So for us to form propane, we need to react carbon and hydrogen to give us propane. This would be the first question, and we would balance with a 4 on hydrogen and a 3 on carbon. The next heat type that has been mentioned in our question is the heat of combustion of propane. So heat of combustion would mean that we burn our propane in excess oxygen. And when we do this, we are supposed to get carbon 4 oxide and water because propane is a hydrocarbon. Now, for our equation to qualify to be heat of combustion, we need to balance this equation as we maintain 1 on our propane. So that would mean a 3 on carbon 4 oxide, a 4 on water, but then a 7/2 on oxygen, so that we maintain 1 as the number of moles of propane being burnt. The next heat type mentioned in our question is the heat of combustion of graphite. And here we shall have carbon, because graphite is carbon, being burnt in excess oxygen to give our carbon 4 oxide. This balances out, so we don't have to do the balancing. Finally, we are supposed to write the equation for heat of combustion of hydrogen. And here we are burning hydrogen in excess oxygen to form water or steam. Here, as we balance, again, we have to ensure we maintain 1 on hydrogen. So it will demand that we balance with a 1/2 on oxygen. These are the 4 equations for the heat changes that have been described in our question. So the next step, as demonstrated in the previous video, is that we should identify one of these equations that can generate the others so that it becomes our main root. And as we can see, this is our equation 1. Equation 1 has carbon, which can generate equation 3. It has hydrogen, which shall generate equation 4, and it has propane, which can generate equation 2. No other equation here has that ability to generate others. So moving forward, we shall write our equation 1 as our main root. So 3 moles of carbon reacting with 4 moles of hydrogen to give 1 mole of propane. Then equation 3 can be generated from this end going down to form the other root to give us carbon 4 oxide. Of course, 3 moles of that. Before we move to the next part, we need to take note that equation 3, as indicated in the values, enthalpy of combustion of carbon is 393 kilojoules negative. This is when we burn only 1 mole. Here we are burning 3. So the amount of heat involved here will now be negative 393 multiplied by 3. To equation 4, which is enthalpy of combustion of hydrogen, we can generate it from this second part of our main root to give us 4 moles of water. Now, enthalpy of combustion of 1 mole of hydrogen is negative 286 kilojoules. But here we are using 4 moles. So this amount of heat must be multiplied by 2. And then for equation 2, we shall generate this root coming down from propane to the products that are formed at this end. Now we know that the enthalpy of combustion of propane has not been given, so we shall represent it as X. But the enthalpy of formation of propane, represented by our main root, has been given as negative 104 kilojoules. So now that becomes our energy cycle diagram, complete with the heat changes in our roots. We proceed now to part 3, or Roman 3 of part C, where we are now asked to use our energy cycle diagram to calculate the heat of combustion of propane. That has been represented by X in our energy cycle diagram. So to obtain the heat of combustion of propane represented by X, we need to identify our initial state of our energy cycle diagram. And here we are. This is the initial state. And you can see all the arrows lead to our final state at this point. So you realize we have 2 routes that can take us from initial state to final state. These 2, root 1 and 104 and X, root 2. By Hess Law, the energy involved in the 2 roots must be equal. So to get X, we shall relate that minus 104 added to X is supposed to give us 3 by 393 added to 4 by negative 286. These 2. So when we work out this, we are able to get X as negative 1179, that is 3 by 393, negative 1144, that is 4 by negative 286, and then we shall add 104. That gives us a value of negative 2219 kilojoules per mole as the enthalpy of combustion of propane. In part D, this tested on fuels, and we are told that other than the enthalpy of combustion, which we also call calorific value, we were asked to state one factor which should be considered when choosing a fuel. And here we have quite a number of factors. There is the cost factor, there is pollution, what we call effect on environment. Then we also have availability of the fuel, availability. We also have storage or ease of storage. And finally we have ease of combustion. Ease of combustion. The final question for number 7 stated that the molar enthalpies of neutralization for dilute hydrochloric acid and dilute nitric acid are negative 57.2 kilojoules per mole, while that of ethanoic acid is a bit lower, negative 55.2 kilojoules per mole. We were told to explain this observation for 2 marks. So we know that ethanoic acid is a weak acid. Ethanoic acid is a weak acid. So being weak, some heat of neutralization is used to ionize our weak acid before neutralization can take place, before neutralization occurs. That's why its heat of neutralization is lower. So we continue that its value of the molar heat of neutralization, is lower than that of either HCl or nitric acid, which are fully ionized, because they are strong acids. That would be our answer for 2 marks. We now cross over to the year 2013, where we are looking at Chemistry Paper 2, question number 2, again testing on Hess Law. This is now the year 2013, Chemistry Paper 2. In question 2, Hess Law was once again tested. So part A, Roman 1, we are being asked to define enthalpy of formation. And enthalpy of formation is the heat either absorbed or evolved when 1 mole of a substance, is in its standard state. 1 mole of a substance in its standard state is formed from its constituent elements. It's formed from its constituent elements. Because of space, I'll write that down here. Is formed from its constituent elements in their normal states. That is the definition of enthalpy of formation. So we proceed now to Roman 2 of part A. The enthalpies of combustion, methane and hydrogen, are indicated below. So we have enthalpy of combustion of carbon is given here, and the equation is already written. Enthalpy of combustion of hydrogen is also given here, and the equation is written as well. The enthalpy of combustion of methane is given as 890, but the equation is not written. So that is what a candidate would begin with. Enthalpy of combustion of methane would mean that we are burning methane, of course 1 mole of it, in excess oxygen, and we shall obtain carbon 4 oxide and water, methane being a hydrocarbon. Now this equation would be balanced with a 2 on oxygen and a 2 on water. As we do the balancing, we have to ensure that it is only 1 mole of methane that is being burnt. So now, armed with these 3 equations, we are asked to draw an energy cycle diagram that links enthalpy of formation of methane to enthalpies of combustion of carbon, hydrogen and methane. So up here we happen to have the enthalpies of combustion of carbon, hydrogen and methane written in equation form, but there is no equation that shows enthalpy of formation of methane. So that is where a candidate was supposed to do some extra work in as well. So an equation that represents enthalpy of formation of methane would mean that we are forming 1 mole of methane from its constituent elements. Constituent elements of methane is carbon and hydrogen. So we would form 1 mole of methane, and we shall then balance with a 2 on hydrogen. So now, armed with the 4 equations, equation 1, 2, 3, and 4, a student was then supposed to look at one of them which should act as the main root, and one from which all the others can be derived. You agree with me that that is equation 4. So equation 1 having carbon will be derived from here. Equation 2 having hydrogen will be derived from here. And equation 3 having methane can be derived from this end. So we shall go ahead and draw an energy cycle diagram with this one as the main root. So equation 1 up here, I can derive it going down to give me carbon 4 oxide at that point. And I know the heat involved will be 393 kilojoules, of course negative. Equation 2 can be derived at this point going down to obtain 2 moles of water. And here I have 1 mole of hydrogen, but here they are now 2. So the heat involved here will be negative 286 multiplied by 2. And coming to equation 3, I will now derive it from that point going down, and I know I will have negative 890 kilojoules of energy. So this becomes our energy cycle diagram, and the enthalpy of formation of methane we do not know. So we shall represent it with X. For 2 marks. Lastly, we were asked now to use the cycle up here to now determine the enthalpy of formation of methane represented by X. So again, this becomes our initial state where all arrows originate. And this becomes a final state where all arrows terminate. So X added to negative 890 becomes our root 1, and the amount of heat spent here should be equal to negative 393 added to 2 times negative 286. When we work out this, we are able to solve for X as negative 393 here added to, or from it we shall subtract 2 times 286, which is 572, and from there we shall add 890. This gives us a value of negative 75 kilojoules per mole as the enthalpy of formation of methane. That marks the end of our video, in which we have reviewed the testing of Hess Law from recent years as far as K.C.S.E exams are concerned. Thank you for being with us, and we ask that you keep it here for more reviews.